Okay, good morning. So, Ms. Pender's been starting with jokes, and I have been neglectful about my Snapple fact. So, I found a fun Snapple fact. I hope I can remember it. So, because it's hard to read from here. So, I think it says in Athens, Greece, a driver's license can be taken away by law if a person is deemed to be either unbathed or not well dressed. Something poorly dressed, that's what it says, poorly dressed. So that was kind of interesting. Not well bathed or poorly dressed. So I'm wondering how many people would have driver's licenses in our country. Okay, so today we're going to solve exponential equations, and we're going to write and use exponential models. So cool stuff today. So let's start off with some nice easy stuff here. Let's do a little quick exploration. So it should be pretty obvious to everyone that 3 squared, which is 9, is equal to 3 squared, which is, well, also 9. And if we wrote this equation right here, 3 to the x power equals 3 to the second power, well, obviously x would have to equal 2 because, right, 2 is equal to 2, x would have to be 2. And things can get a little more complicated if we just, make a little more complicated expression here. So let's say we have 3 to the 2x minus 8 equals 3 to the 2. Well, all we need to do is set the two exponents equal to each other, just like we did here. Set x equal to 2, and we have our answer. So we're just going to set that equal to 2. We'll do that work right over here. So we get 2x minus 8 equals 2. Add 8 to both sides, so we get 2x equals 10, or x equals 5. And that's the answer to that equation right over there. And so, here's the rule. In order to solve exponential equations, you just need to make the bases the same, and then set the exponents equal. So make the bases the same, then set the exponents equal. All right, so let's start with this one right here. So we have 4 to the 3x minus 1 equals 16. Well, these bases aren't the same like these are, right? These are all 3's, so these two guys are not the same, and I wonder what base we could use to make them have the same base. Well, I know that 16 is the same as 4 to the second power, and this is already 4 to the 3x minus 1 power, so 4 is a really good base here. By the way, we could also have used 2, but I think 4 is going to work great here. So 4 to the 3x minus 1 equals 4 to the 2. So now we have the bases the same, and that means all we need to do is set the exponents equal to each other. So we get 3x minus 1 equals 2. Add 1 to both sides. We'll do that work right up here. So we're going to add 1 over here, so it's going to make 3. So 3x equals 3, or x equals 1. And there it is. It's that simple, right? Just make the bases the same, set the exponents equal, boom, solve the equation, easy stuff. Okay, so let's jump over to this one right here. Very similar sort of problem. And we see that we have 5 and we have 625. This ends in a 5, so that means that this probably's got some 5 something going on here. As it turns out, 625 is 5 to the 4th power. So we have 5 to the 3x plus 10 equals 5 to the 4. We have the bases the same. Now we just need to set the exponents equal to each other. And we get 3x plus 10 equals 4. And we subtract 10 from both sides, and we get 3x equals negative 6, or x equals negative 2. So sometimes we can have a positive number, sometimes we can have a negative number. We could also have fractions or decimals. All of those things are totally fine in these problems. All right, so let's look at this one right up here. So we got now both sides having an exponent with a variable in it. So again, we just need to make these guys have the same base. And as we look at this, previously we just said, okay, well, 9 is here. Well, this must be 9 to some power. Well, that's not true, because 9 to the first power is 9. 9 to the second power is 81. We went right by 27, so that can't be it. So let's think about this. Is there a number that we can raise to a power that makes 9? And if we take that same power and raise it to same number and raise it to a different power, will it make 27? And the answer is yeah, there's definitely a number like that, and that number is 3. So 9 is the same as 3 squared, 27 is the same as 3 cubed. So we're just going to replace the 9 with 3 squared to the 2x minus 1. And 27 is 3 cubed to the 3x plus 6. All right. Now, we remember our laws of exponents. And we remember when we have a power to a power, we multiply the exponents. So we're just going to multiply 2 by that using the distributive property. So we'll have 3 to the 4x minus 2. And this is, same thing, distributive property here. So 3 times that stuff. 3 to the 9x plus 18. And so now the bases are the same, which is what we tried to accomplish. Therefore, all we need to do is set the exponents equal. So we got 4x minus 2 equals 9x plus 18. And let's finish the problem over here. Finish it right there. So we're going to subtract 9x over there to get negative 5x. We're going to add 2 over there to get 20. So we get negative 5x equals 20. Divide both sides by negative 5. X equals negative 4. Just like I said, we can have negative numbers or positive numbers, or maybe even some fractions. Speaking of fractions, here they are. So we see 1/8 and we see 1/16. And again, we think, well, is there a number that we can raise to a certain power to make 1/8 and the same number to a different power that makes 1/16? Well, I know that 2 times 2 times 2 makes 8, and 2 times 2 times 2 times 2 makes 16. So 2 seems like a good base, but how do we raise a base to a certain power to make a fraction? Oh yeah, negative exponents. Negative exponents give us fractions. So 1/8 is really the same as not 2 to the third, but rather 2 to the negative third. Because remember, anything to a negative exponent equals 1 over that thing to the positive exponent, which gives us the fraction here. So this is going to be 2 to the negative third power, which is 1/8, to the x plus 1. And here we have 1/16. Well, that's 2 to the negative fourth power, because 2 to the fourth is 16, but it's 1 over that, so it must be 2 to the negative fourth. And we get 2x minus 3. And again, we have the same basis now. And we raise a power to a power. That means we multiply the exponent, or the exponents. So we get negative 3x minus 3. We multiply here. Negative 8x plus 12. And we're going to add 8x to both sides. So let's add 8x here and 8x here. So that'll get us 5x minus 3 equals 12. Add 3 to both sides. Finish that right over here. And so we're going to get 5x equals 15, or x equals 3. I've not done a very good job of making sure we get some fractions or decimals in here, but I'm telling you, we can get fractions or decimals. That's totally okay. All right, so again, the moral of the story here is make sure you get the bases the same. And then for these a little more advanced equations, we need to make sure we multiply the exponents together. Power to power means multiply. And then we set the exponents equal. Okay, so let's move on to exponential models. And this is very pertinent right now for this time in our world, because lots of things grow exponentially. Populations grow exponentially, like populations of cities, populations of bacteria, number of people with a certain virus. All of these things tend to grow exponentially. And so it's good for us to know something about an exponential model. And remember, of course, from what Ms. Penter said, an exponential function is a function in which we have the variable in the exponent place. So I would just want to expand that a little bit. So here we have y equals a times, right, a times b to the x. And in our model here, a is our initial value, the amount that we're starting with. And again, that could be a certain amount of money, or it could be a certain number of people infected with a virus, which is actually the problem we're going to look at in just a moment. And this is our growth factor. And our growth factor is related to how quickly something is growing or actually decaying. Some things actually don't grow exponentially, but they decay exponentially, like perhaps the value of a vehicle or something like that. You know, it starts off high and gradually gets lower and lower and lower. So let's take a look here. And this is actually some real data that I took off of the New Hampshire, not Board of Health, but the New Hampshire website, one of the New Hampshire websites. So on a certain day in New Hampshire, actually March 23rd, 101 people had contracted a virus. Well, at least that's how many they had tested positive. A week later, literally a week later, 314 people had tested positive. And I want us to be able to write the model and then use the model to predict how many people would be infected in a month. In other words, 30 days from March 23rd, which actually happens to be April 22nd. And hopefully I still have the actual data here. Yep, I do. Right here. The data. So we'll be able to compare the data in just a minute. Okay, so let's set up our model here. So here it is, y equals a times b to the x. We're going to flip. Nope, we're just going to change our page here. So we have y equals ab to the x. And so we know that our starting value is 101, right? That's how many we started with. So we're going to write y equals 101b to the x. Now we have too many things here that we don't know. It's okay that we don't know y and x, right? Like we're accustomed to having y equals 3x plus 1 or y equals 1/2 x minus 7 or something like that. That's totally fine, right? We got a y and an x, that's good. But we need to fill in these numbers here, right? This is like y equals mx plus b, and you know, we need to find b in this case. So we're going to find b by using this other piece of data right here. This guy right here is a second piece of data for us to help us to find the value of b. So it says 7 days later, there are 314 people infected. So x is 7, y is 314. So we're going to put that stuff right in here, and we're going to figure out what b is. So 314 equals 101 b to the 7th. So in order to solve this, we need to divide by 101, so we can isolate our special term here, right? B to the 7th is our special term. So we're going to divide 314 divided by 101. So I'm going to do that right here. So 314 divided by 101 equals 3.1089. So I got 3.1089 equals b to the 7th. So now we need to get rid of this 7th power thing here, and if this was b squared, we would take the square root of both sides. If it was b cubed, we'd take the cube root of both sides, but it's b to the 7th, so we're going to take the 7th root of both sides. And the easiest way to take the 7th root on your calculator is raise something to the 1/7 power. So we're going to raise both sides to the 1/7 power. 1/7 equals b to the 7th to the 1/7, which by the way is just b, right? Because 7 times 1/7, right? Power to power means multiply, so 7 times 1/7 is b to the is 1, so that's b to the first, or just b. So b is going to be the 7th root of that thing right there. So I'm just going to do that with my calculator. I'm just going to raise that number to the, and the way I do that is I make a parentheses. Can you actually see this? Yeah. So I make a parentheses, and then I do 1 divided by 7, and I close up the parentheses. Right, so you can see that the answer, which is what I had before, 3.1089, I'm going to take the answer and I'm going to raise that to the 1/7 power. I'm going to hit enter, and there it is, 1.1759. I'm going to use 4 decimal places here just so I can be a little bit more accurate. So 1.1759. So now I know that b is 1.1759. So b equals 1.1759. So then our model is y equals 101, that's the starting value, times 1.1759 to the x. So this is our model for the data that we had for that 7-day period right there. Now, I've kind of run out of room here a little bit, but that's okay. I'll just move right over to here. So now what we're going to do is we're going to use this model here and figure out how many people would have contracted the virus or tested positive for the virus in 30 days if this had continued. And so what we're going to do here is we're just going to take 30 days, put it right in there, so 1.1759 to the 30th power get some answer, and raise that and multiply that by 101. So we're going to have y equals 101 times 1.1759 to the 30th power, right? Because that's how many in 30 days? 1 month later. 30 days. 30 days right there. So I'm just going to do the work on the calculator here. So 1.759 to the 30th power is 129.175. 129.175. 101 times 129.175, right? And then I multiply that by 101, and we get 13,046. Actually, round it up, 13,047. 13,047. So in a month, according to that model, there should have been 13,047 people infected on, what was that day that we were interested in? 1 month later, which is 1 month after March 23rd, is April 22nd. So April 22nd, according to our model, that's what we would have, 13,047 people. But for real, the real data here, I have the real data here, 1588. The real number is actually 1,588 people. So, what does that mean? Does that mean that our model was terrible? No, that means that our model was actually really good, but our model did not take into account, because you may remember that our whole story here started here right on March 23rd, right? That's when we had our little bit of, that's our starting data point. And you may remember that we stopped going to school on March 16th. That was a week before this. And so, what that means is that for a few weeks here, we started right away doing the social distancing, the wearing masks, the not going to school, the staying home, all that sort of stuff. And because we did that, we avoided this number here, right? Because if we hadn't changed what we were doing, this is what was going to happen. But because we changed what we were doing, this is where we were. A lot fewer people ended up being infected with this virus based on the changes that we made. So, whenever, the next time you're wondering, when is math ever useful? Here is where math is really useful. So, okay, enough on that. And so this is actually a very real problem, and epidemiologists are using exponential growth models all the time. And we got a chance to actually do some real math right here in front of your very eyes. Okay, so that was some real data here, and I'm just going to make up some stuff right here. So let's say that we started with 7.2 whatever, something, $7.2 million, right? Maybe this is a company, and 3 years later, the company was worth $50 million. Write the model. So, easy enough. So we now know that our model for exponential growth always looks like this: y equals ab to the x. And in this case, a, of course, is the starting value, and the starting value always happens at 0, right? So we're going to have y equals 7.2 b to the x. So that's our first data point. We use that data point to get us this, because it starts at 0, right? That's when we start. And then we're going to use this data point to get us the value of b. So the x value is 3, the y value is 50. So that's how we're going to calculate b. So we got 50 equals 7.2 times b to the 3. And as always, we want to, because we're solving, we want to isolate the special term here. So we're going to divide by 7.2. So 50 divided by 7.2 is actually going to be really close to 7.2. It's going to be 6.94 repeating. So we now know that 6.94 repeating equals b cubed. But of course, we're not interested in b cubed. We just want b. So that means we need to cube root both sides. And the way I'm going to cube root is I'm going to raise this to the 1/3 power, right? Cube root, 1/3 power. Fourth root, 1/4 power. Square root, 1/2 power. So I'm literally going to do that right now, right? So I got 6.94 repeating. There it is, 6.94 repeating. And my little cursor's down there. So I'm going to raise that to the, what did I say? 1/3 power, right? Because it's cube root, so I'm going to raise to the 1/3 power. So I'm going to get my parentheses. I'm going to do 1 divided by 3, which as you can see makes 1/3. 1 divided by 3, 1/3. Close the parentheses, hit enter, boom. 1.09785. I'm going to call that 1.079. 1.079. So B equals 1.079. So then our final model here is y equals, where am I? 7.2 times 1.079 to the x. And there's your model right there. Okay, so here's the cool thing. Money also grows exponentially according to this formula. A, the amount at the end. So this is the amount at the end, equals P, this is our starting amount, also known as principal, P-R-I-N-C-I-P-L-E, not P-R-I-N-C-P-A-L, right? That's the guy in the main office, Mr. Ernest. R stands for our, right here, R is our interest rate. This is the percent that our account is growing at. N is the number of times compounded. I'm just going to write it down here. Compounded each year. And T is the amount of time in years. T for time. And it's a number of times compounded each year. So that means compounded means how often are we calculating the interest. So we could calculate the interest once a year, which is annually, twice a year, biannually or semi-annually. We could do quarterly, 4 times a year. We could do monthly, 12 times a year, right? And it would be 12 in that case. We could do it daily, 365 times. We could do it weekly, 52 times, right? So, and it's just the number of times that we compound or calculate the interest in a given year. So R again is the interest rate, and is the number of times that we calculate that interest on the amount that we have invested, the principal. So let's do a problem with that. It's really simple. It looks complicated because there are a lot of words here, but really we just take out one formula to work with. And that formula again is A equals P, 1 plus the interest rate over the number of times we compound the interest or calculate the interest, times T. Number of times per year times the number of years. All right, so Bob the Builder is considering retiring in 20 years. I mean, he's been working a lot. He's earned his time to retire. He decides to invest $10,000 right now in an account that pays 6% and is compounded monthly. In other words, the interest is calculated every month. How much will he have in his retirement account at the end of 20 years? Well, easy enough. Plug the numbers in. Calculator does the work. So the amount at the end of the 20 years is going to be 10 G's, right? He's done a good job saving his money. He's a smart guy. 1 plus R, the interest rate is 6%. Whenever we calculate with percents, we always change them into decimals, move the decimal place over twice, 0.06, divided by the number of times it's compounded per year. In this case, it says monthly. There are 12 months in a year. And it's n times t, so 12 is still the number of times, n is still 12, right? Those two numbers are the same. And t is time, and that's 20 years. So we're just going to use our calculator to do the rest of the work here, pretty much. So 0.06 divided by 12, and that should be easy enough, right? It's going to be 0.005, but we'll just make sure. 0.06 divided by 12 equals, yep, 0.1005. I'm sorry, 1.005. 12 times 20, of course, is 240. And so now we just raise 1.005 to the 240. So raise to the 240 power. And we get something bad. 12 times 20 equals 240. All right, good. So 0.005. Oh, that's 1.005. There we go. 1.005 to the 240 power equals 3.3102. So 10,000 times 3.3102. So we multiply that by 10,000. So we got 1, 2, 3, 4 zeros. Move the decimal place 4 times. 1, 2, 3, 4 times. So we got $33,102. So Bob the Builder is going to have $33,102 at the end of his 20 years of investing. So he just drops the money in there, $10,000, keeps working for 20 years, comes back 20 years later, and he's now got $33,000 in his account. So there you go. There's exponential growth. And yeah, so we will see you on Wednesday. Be safe.